Rock, paper, scissors. A timeless classic we've all played at some point, whether it's to settle a bet, make a quick decision, or even just for fun. But the balance of this game raises an intriguing question. Why are there only 3 options? Why not 4 or more? What we're going to do today is explore the mathematics behind rock, paper, scissors and learn why 4 options is mathematically unfair. In order to do that, we'll first have to define what it means to be mathematically fair in terms of rock, paper, scissors. By definition, rock, paper, scissors is a zero-sum game, which essentially means that one person's loss is another one's gain. What this means is that if we thought of the game in terms of points, a tie would represent a point change of 0, a victory would represent gaining a point, and a loss would represent losing a point. Now for the first condition that must be met in order for a rock, paper, scissors game to be considered fair. The expected point change in each round must be equal to 0. This is clearly evident in a rock, paper, scissors game with 3 options, where there is a 1/3 chance to tie, a 1/3 chance to win, and a 1/3 chance to lose, summing up to an expected point change of 0. From this condition, we can also conclude that for each option, the number of ways to win must be equal to the number of ways to lose. This is because each tie is weighted as 0, so the probability of winning for each choice must be equal to the probability of losing. The second condition is a much more conceptual one. Each selection may only tie with itself. In the game of rock, paper, scissors, each option ties with itself because they are identical in their properties, making neither option superior or inferior. It would only be right to maintain this property as we add more options. Also, let's say for example you had a 4th option, like a stick, that tied with all other options. This 4th option would essentially ruin the balance of the game by removing any risk from the game. Now that we understand what it means for a rock, paper, scissors game to be considered mathematically fair, we can start to understand why 4 options is mathematically unfair. Consider a rock, paper, scissors game with 4 options, A, B, C, and D. Let's say we select option A. Of course, option A will tie with itself. Now let's say it wins against B and loses against C and D. It is clear that there is a higher probability for A to lose. Another example would be if A lost against B, won against C, and then lost against D. For both these examples, it is clear that A has a higher probability of losing. If we calculate the expected point change, we can see that it is in fact not 0, breaking the first condition. Now let's extend this idea to an n amount of options, where n is any even positive integer greater than 2. There are n outcomes for each selection, and removing the tie outcome leaves n-1 outcomes for each selection. Also, according to the first rule, the outcomes that result in a loss must be equal to the outcomes that result in a win, meaning that there must be n-1/2 wins and n-1/2 losses for each selection. This means that n cannot be even, as it will be impossible to have an equal win-to-loss ratio for each selection. Now let's store that idea away for later and discuss a rock, paper, scissors game with an odd amount of selections. Again, let's assume that you have n selections, S1, S2, all the way to Sn, but in this case, n is odd. There are n squared outcomes in total, as there are n ways to choose the first selection and n ways to choose the second selection. N of those outcomes will result in a tie, leaving n squared minus n outcomes that result in a win or a loss. Since the wins and the losses must be equal for it to be fair, there are n squared minus n over 2 wins and n squared minus n over 2 losses. Now this fraction looks a lot like the amount of ways to choose 2 distinct options from n options disregarding order, and that's exactly what it is. The number of outcomes that have to result in a win or loss is equal to the number of ways to choose 2 distinct selections from n selections disregarding order, making it possible for all odd n to design a rock, paper, scissors game that is mathematically fair. A perfect example of a 5-option rock, paper, scissors game is the one from the television show The Big Bang Theory. Rock, paper, scissors, lizard, Spock. This version of rock, paper, scissors is perfectly balanced so that each option only ties with itself and the number of wins is equal to the number of losses. When you play rock, paper, scissors next time, whether it be to settle a bet or to kill some time, introduce another option or 2. Make it mathematically unfair. Challenge the norms. With math, anything is possible.